Swayam Prabha. Digital India. Educated India.
Now, we have done a kind of a summary of how materials have evolved. As of now, in today's scenario, if you want to take a stock of that what are the materials there in front of us, it is better to categorize them, because there are many materials. Okay. So, if I think of categorizing the materials, then first thing that I can do is that I can keep the metals and alloys separately. That is one group. Okay. So, starting from the metal age onwards, that is continuously happening. Then I can keep the non-metals, and in fact out of the non-metals I would say that I can actually go for ceramics and then the polymers, and then I can make composites. Composites are, of course, it is either made from between two polymers, polymer ceramics or metal ceramics, all sorts of things. Okay. So, basically if we think of it that we can keep it as a basic subdivisions of metals and non-metals, and further the non-metals in terms of because the non-metals generally only talk about basic elements, but instead of that we can think of the kind of suppose oxides of various types like the ceramics or the polymers or the composites. Now, among the metals also you have the ferrous metals like iron, steel, and you have non-ferrous metals. As I told you that the aluminum, for example, titanium, okay, they play a very important role in terms of the lightweight category of aircraft alloys. For aircraft alloys, they play a very important role. Okay. Then of course, limited amount of copper and zinc, etc. Tungsten, again for very high temperature applications, it is very good. So, there are non-ferrous which have uses in certain very specific applications. So, I would rather say specific and high performance applications. That is where you need actually the non-metals other than aluminum, these titanium, tungsten, vanadium, molybdenum, chromium, etc. Okay, for these type of things. Okay. Now, how about the ceramics? Ceramics, they are more like in the form of I would say particle or fibers, which are used in terms of making either composites or making ceramic products. So, alumina, silica, silicon carbide for example is very widely used in making tools. Alumina and silica has a very wide application in terms of refractory bricks, etc. Diamond is one ceramics which of course has some applications in the ornamentations and some applications in terms of cutting tools, because that is one of the hardest material. Then in the polymer, again you can actually subdivide it into certain things like natural polymers like say wool or silk, and polymers which are synthetic, that are human created like polyethylene. This is polyvinyl chloride which is used for all your PVC pipes, is very popular. Nylon, I told you in the very beginning of polymer adventure, nylon was one of the first products which was used in developing parachutes, for example. Then bakelite which is used for making insulating materials for electrical applications. So, that is about the polymers. And then if we talk about the composites, then we have wood as a natural composite, okay, and then we have concrete, we have fiberglass, we have CFRP and GFRP. CFRP and GFRP, the full form are carbon fiber reinforced plastic, that is CFRP, and GFRP as the glass fiber reinforced plastic. Same thing, the reinforced plastic. So, these are various types of composites which are very widely used. There are many in fact, but that is the kind of a broad classification that we have in terms of the engineering materials that are available today. So, let us try to classify them. There is this very famous pentagon that is developed by Ashby. You will see it in his material selection in mechanical design book, where he has given these very nice circles of materials like metals, for example, the steel, cast iron, aluminum alloys, copper, zinc alloys, titanium alloys, and then if you come to the other vertices, so one by one let us explore the vertices. So, metals, that is fine, all these things together. If you come to the polymers, then you have something like polyethylene, okay, high density or low density polyethylene, which is used in terms of making carrying bags, for example. Polypropylene is used for making various types of things which can resist a high temperature like feeding bottles. PET and PEK, that is polyethylene terephthalate or polyethylene ether ketone, they are used in this mineral water bottle context, right. And then polycarbonate is used in terms of once again making high performance polymers like transparent polymers. Polystyrene is used again for high performance polymer, and polyaniline is one of the polymers which is actually a conductive polymer. So, for conductive series of polymers they have a very high use. Then it need not be that the polymers are only used for structural materials. So, these are for making products, but they are also used in terms of polyesters, which is like in terms of fibers. They are also used in terms of resins. These resins are used as matrices actually. So, these are used as matrices for composite materials. So, that is what is the world of polymers. Now, naturally elastomers are also polymers, but they are separated out from this list because they are very specifically designed for certain purposes. One of them is shock and vibration absorption. With the advent of, you can say that the automobiles and all the transport sector, shock and vibration becomes very important, because any machine or mechanism has a shock and vibration problem. So, to actually absorb that, you would need some kind of a material which can dissipate lot of mechanical energy in the form of thermal energy, etc. Now, natural rubber was the first candidate towards that direction, but since in nature you get only a limited amount of it, so then all other synthetic rubber started like butyl rubber, and then other elastomers like neoprene, isoprene, then the silicones, etc. So, this actually developed a group of elastomers, and one way in which the elastomers are characterized is that if you think of metals, for example, what is the typical, I will talk about this later on, but maybe I will just introduce at this stage that if you look at the stress strain diagram for the metal, you would see that it goes straight like elastic and linear, then it actually has a yielding and then it goes down. And this is generally, this linear level is about 0.1%. On the other hand, if you look at the elastomers stress strain diagram, how would it look like? You would see that it is non-linear, but it will go up to a very large extent before failure. So, this is something like, you can say something like 10%. So, that is the kind of stress strain behavior we are talking about. So, elastomers in comparison to the metals can deform a lot, large deformation. That deformation may be non-linear in nature, but you can, the deformation is still elastic. That means once you withdraw the force, you can actually recover back that deformation, and that is very good in terms of high stretchability. So, that is used for various applications. Now, the other part of the side of the pentagon is actually ceramics and glasses. Often we talk about them together, but they are not really together, because when we talk about ceramics, ceramics have, at a later stage I will tell you, they have a very regular crystal structure. So, hence, and on the other hand, glasses are completely amorphous, they are very irregular in terms of their structure. So, that is why ceramics and glasses, even though both of them are very same, as per your daily experience, you can see that if you put a glass bottle, if it falls down, it breaks into pieces, and same thing happens for a ceramic pots. So, ceramics and glasses share a very common property, that both of them are very brittle in nature, but even though they are brittle in nature, their basic microstructure are actually different. For ceramics, as I told you, that you will get a very regular atomic structure, crystal structure. On the other hand, glasses you will not get a regular crystal structure in it. So, in the ceramics, there is these groups of alumina, which is used mostly, I told you, in terms of making fibers either, or in terms of refractory bricks. Then there is silicon carbide, which is also used in terms of making tools, and then zirconias is a wonderful element which is also used for making something like the piezoelectric materials, some kind of a lead zirconate titanate. So, and kind of a hybrid of this zirconia, advanced ceramics, one of the advanced ceramics, they are used. Also in other cases, zirconia has certain phase transformations which are very good and can be used in terms of developing toughness into a system. Then there are glasses, and based on the origins there are these soda glass, borosilicate glass, silica glass, glass ceramics, etc. So, glasses of course is very important because of one of the very important property that they are transparent in nature, and that means they can be used in terms of manipulating with the light waves in various forms, for focusing the light waves in the form of lenses, or for passing the light waves, or for concentrating it in the form of lasers in various other systems. So, that is the domain of engineering materials, and you can even have hybrids from taking contribution from each one of them, like composites, like sandwiches, various types of segmented structures, lattices or foams, etc. And we will venture into all these gamuts of materials as we will be progressing in our lecture. Now, when we talk about metals, this is very well known to you, but let us just recapitulate, because this is an introductory lecture. What do we mean by these metals? What are the basic physical properties? Like when we talk about metal, they have a very good electrical property or heat conduction. They are very malleable. You can make you can make a thin film out of, beat them into a thin sheet. They are very ductile. they process something called a metallic luster, that is why some of the metals are used for ornamentation. They are generally solid at room temperature except mercury. And in terms of the chemical property, what you would notice is that they are very, I would say, benevolent or kind in terms of giving away their electrons. They lose their valence electrons very easily. That is why the metals actually form some kind of a, a kind of a cloud of electrons from all the metallic atoms together, and hence there is a pool of electron which is constantly available to conduct electricity. That is what is the good part of it. Now, they form the oxides which are basically basic in nature. The easiest example is the calcium oxide that that you get when you take actually these pans type of things. Okay, that is the basic in nature. So, similarly all metallic oxides are basic in nature. They are basic and hence they are good reducing agents, okay, because they losses electrons and they have lower electronegativity. So, the tendency to attract the electrons, because they are lower electronegativity. So, that is something that you will see is more in terms of the non-metals. So, that is what is our the group of metals. Now, if you look at the non-metals, then whatever metals do not have, most of the things non-metals are having. They are poor conductor of heat and electricity, and they are very brittle, and they are non-ductile. You cannot really, they are not malleable, you cannot make very thin sheets out of it. They do not generally, they do not possess metallic luster, that is for sure. Some of them, like for example these this kind of crystals like say diamond for example, or some such things, they actually have a very high degree of internal reflection, and hence they create a kind of a luster. It is not metallic luster, but it is generated because of that internal, total internal reflection as we call it. They are many a times transparent as a thin sheet. They are available, unlike the metals, as solids, liquids and gases at room temperature. In all the phases you will find them. Usually they have 4 to 8 electrons in their outer shell, and then they form oxides that are acidic in nature. So, unlike metals which forms oxides which are basic in nature, they are, that is why good oxidizing agents, and they have a much higher degree of electronegativity. So, that is the nature of the non-metals. Then specific group of non-metals, I would say, is the ceramics. So, these are inorganic materials in which basically both metals and non-metals come together, and mostly they are, for example, oxides, okay, the iron oxides or the carbides like the silicon carbide. They are formed by the action of heat and subsequent cooling, and they are generally brittle in nature, and they are good insulator of heat and electricity. They have excellent compressive strength. That is why you would see that most of the earlier structures, like you consider pyramid or you consider the domes, they are actually made of ceramics because they have excellent compressive strength. In fact, you see that some of the applications here like the roof tiles or the bricks, where it is the compressive strength which is explored. On the other hand, certain very interesting applications are there. For example, in the turbine blade, here it is the high temperature properties that they do not creep very easily. So, at the high temperature they maintain the geometric shape. So, that is explored in this context. Potteries, once again they are basically explored in terms of that they do not react much. So, you can actually put lot of materials into it, and you can use it in terms of storage system. And in terms of bearings, it is the frictional property that is utilized, because you can have ceramics which can have a very low wear and tear. So, that is very good in terms of the frictional property. And in terms of electric insulators, you must have seen these examples where it is the insulation property, the electric insulation property that is utilized. So, thus there are many interesting areas where ceramics are having truly, I would say, unique applications. Next comes the polymers, natural rubbers. That was the once upon a time the only polymer, but then there are many other things, wool, silks, etc., and then synthetic polymers. I talked about it, synthetic rubbers, bakelite, neoprene, nylons, etc., and the whole world today is around the polymers. So, I will more describe about the polymers later. The composites. In the composite, the idea is that it must have two or more constituents, in which one is the major constituent, which is like the matrix, and the other one is a minor constituent in terms of the volume fraction or the weight fraction, but it is not a minor constituent in terms of strength or in terms of the modulus of elasticity or in terms of other interesting properties like high temperature performance, etc. So, that is the idea in the composites, that you mix two materials, basically you mix one extra material on a matrix to improve substantially the property of the basic material. Consider, for example, like this is an aircraft. Okay. So, for this aircraft, if you look at the wing part of the aircraft, there you will see the maximum use of the composite. So, these red areas, they are generally of carbon fiber reinforced plastic. Okay. Then you have other areas where you will see that like the belly part of it or the wing tip part of it, where you will see that the Kevlar is used. Then you will also see this kind of a thing in the tip part of it. In the high temperature zones, you may see like this close to the engine, that there is this Kevlar sandwich with stiffening carbon plies. And in certain less important areas in terms of structural strength, but very important as a connecting material, you will see fiberglass is used. So, one of the two advantages that composites gives us is in terms of what you call the lightness and in terms of the strength and modulus of elasticity. So, we actually say this in terms of specific stiffness. Specific stiffness means modulus of elasticity per unit density, and specific strength. So, that means once again with respect to the weight, the stiffness that you get or the strength that you get is very high in the composites. Thank you.